Hello, everyone. Today we're going to start talking about the information that you should find in Chapter 3 of your textbook, which is on the composition of substances and solutions. We're going to start out really easily in Chapter 3 by talking about how you calculate formula mass. And what you've got to remember is that when you're looking for formula mass, you're going to go to the periodic table and use the mass from the periodic table. So if I were to ask you to find the formula mass for the compound H2O, how would you do that? Well, all you would do is go to the periodic table and get the mass for 2 hydrogens and 1 oxygen. Now, I highly recommend that you round your masses to 2 places after the decimal. That's how I will do all of my assignments, is rounding them to 2 places after the decimal. Your book will sometimes use more than that, but for all the problems that I'm doing, I will be using 2 places after the decimal. Now, when you add those numbers together, that will give you your formula mass for your compound. So no matter what elements are in your compound, all you're going to do to find the formula mass or the formula mass for your compound is actually get the masses for those elements from the periodic table. After your book talks about formula mass, it then moves into the concept of the mole. Because what we find is that 1 mole of any substance will be equal to its mass from the periodic table. So if we're talking about a mole of carbon, we generally say a mole of carbon has a mass of 12.01. And again, that value is the mass of carbon on the periodic table. If we're talking about a mole of water, we would say a mole of water has a mass of 18.02. And usually when you're talking about molar mass, the units for the molar mass are grams per mole. With formula mass, if we're talking about individual elements, then we say the units are AMU. But when we move to molar mass, where we're looking at how much is the mass of 1 mole of a material, that's when it becomes grams per mole. Now, this is really important because 1 mole of a material, and again, please remember that a mole is a quantity, just like the term dozen means 12, the word mole means a quantity, and that quantity we call Avogadro's number. That quantity is represented as 6.022 times 10 to the 23rd. So that amount of any material has a different mass, and the only reason it has a different mass is because each of those elements has a different mass. And so you will need to be able to do conversions where if I give you mass and ask you how many moles, you'll have to use the molar mass to be able to figure that out. And remember, you're going to set it up using dimensional analysis, just like we've done before, and get your units to cancel out to determine how many moles there are. So if I gave you a problem that said I had 3.24 grams of beryllium and I wanted to know how many moles that was, if I gave you a problem, again, that said that I've got 3.24 grams of beryllium, and I want to know how many moles that is, then again, we're going to set up a dimensional analysis problem just like we've done in the past. So we would start with what they gave us, which is the 3.24 grams of beryllium. We set it up so our units cancel out. So I need grams of beryllium on the bottom, and I need moles of beryllium on the top. Now, in your dimensional analysis problem, anytime you see the units grams, you're going to go to the periodic table to get that value. So when we go to the periodic table, we find out that the mass for beryllium is 9.01, and this is for 1 mole of beryllium. And so when I do the math, what I'm actually going to end up doing is I've got to do 3.24 divided by 9.01. And when I get that value, I find out that that value is about 0.36 moles. And so again, nothing changes with how we do the dimensional analysis. You just got to remember what your units are and what you place where. Again, if you have mass, that mass is going to come from the periodic table. And you find that by adding up the masses of the elements that are in your compounds. So that's one kind of problem you're going to see in your textbook. Another kind of problem that you're going to see in this chapter is if I give you the mass and I ask you for the number of particles. And when we say number of particles, again, we're talking about Avogadro's number, but remember, each mole of a material has a different mass. And so when you do a conversion, if they give you mass and they ask you for particles, then you've actually got to do a couple of steps. The conversion we know takes us from mass to mole, but we also know a conversion that takes us from mole to the number of particles. And so we would have two steps in our problem. But when I say particles, what terms am I referring to? And the biggest thing that you need to remember is that there are 4 different kinds of particles that you can have. The 4 kinds of particles will depend on what whatever the substance is. So when you've got elements, your kind of particle is an atom. When you have an ionic compound, you could be asked to find the number of ions, or you also could be asked to find the number of formula units, which the smallest part of an ionic compound is called a formula unit. Or if it's a covalently bonded compound, then they could ask you to find the number of molecules. So your 4 particle terms are atoms, ions, formula units, or molecules. So if you see any of those terms are all your particle terms. And so you would need to incorporate Avogadro's number. Or if they gave you a problem where they gave you mass and they ask you to find the number of particles, then you would still have to incorporate Avogadro's number in finding your answer. Now, please make sure you remember how to enter your scientific notation in on WebAssign, because you don't type it the way you would write it out. So make sure you check that, and if you've got questions on that, please let me know. In the next section in chapter 3, that's where we start talking about our empirical and molecular formulas. Please remember, when we deal with empirical formula, the empirical formula is the simplest whole number ratio of particles. So if we were dealing with glucose, and if you remember the formula for glucose, glucose is C6H12O6. Well, that's the molecular formula for glucose, but that's not the empirical formula for glucose. The empirical formula for glucose is actually CH2O. All right, and we got that by dividing each one of those subscripts by the same value, and so we got the smallest whole number ratio of those elements to one another. That's what we mean when we say empirical formula. Our molecular formula, again, is the actual formula that you actually have. And now these are important because the empirical formula can help us determine what our molecular formula is, but lots of compounds can have the same empirical formula, but only one compound can have the same molecular formula, and that's the same compound. All right, and so the rules that you need to remember when you determine empirical formula, there are 4 steps that you need to do to find your empirical formula. The first thing is you read your problem and see if they gave you percents. And I usually use this little poem to help with us doing these conversions. The first line of the poem says percent to mass. So if they give me percents, then I change those percents to mass. How do I do that? Well, instead of the percent sign, I write a G because we're assuming that we have 100 grams of whatever our sample is. All right, so I change any percents I have to mass. And then, just like we did before, line 2 of the poem says we change our mass to moles. So once we have our masses, we change the mass that we are given of a particular element to the number of moles of that element that we have. The third line of the poem says divide by small. So once I have converted all of the masses to moles, I look at the number of moles and I see which number of moles is the smallest. And I divide each one of those number of moles by that smallest value. And then the fourth thing that we have to do, or the fourth line of that poem, says that I multiply until I get all whole numbers. So don't round your numbers off to things that don't make sense. Please make sure that you are aware of your equivalents that you need. So like, what is the decimal equivalent of, or what is the fractional equivalent of, let's say I've got something that is 3.1. So how would I write that 0.1 as a fraction? And the answer is you would write it as a mixed number, and that mixed number would be 3 and 1 over 10. Or if it were 3.2, you would write it as whole number 3 and then 2 over 10, but you can reduce the 2 over 10 to 1 over 5. So you need to be familiar with your equivalents. You need to know your equivalents for your halves. You need to know your equivalents for your thirds, your fourths, your fifths. You need to know them for your ninths, and you need to know them for your tenths. Okay, because you cannot just round those numbers off to just random numbers. You need to round them or approximate them to what they are approximately equal to. So like if you get something like 3.72, then you would expect that that would be like 3.75, and you would write that as 3 3/4. All right, so if you have any questions about that, please let me know, reach out. But once you are able to find the empirical formula, you can use more information to find the molecular formula. So what you're going to do is, once you know what your empirical formula is, your job is to figure out what the molecular formula is, and you'll do that by finding the molar mass for the empirical formula you just found. And they're going to give you the molar mass for your molecular formula in your problem. And so you just need to divide those two numbers. You do the molecular mass for your molecular formula on the top, and you divide that by the molecular mass for your empirical formula on the bottom. That will give you a whole number, and you need to take that whole number and multiply by each of the subscripts for your compound to find the correct molecular formula. Now, again, it does take a lot of practice to do this. There are lots and lots of examples given in your book in section 3.2. If you have any questions on what you find there, please let me know. And so that half of the chapter covers how we do the composition of substances. The last half of the chapter deals with how we find the composition of solutions. And so in section 3.3, that's where we start talking about molarity, and molarity is one of the most important topics that you'll cover in chemistry. Please remember the definition of molarity. We always defined molarity as the number of moles of solute in the liters of solution. All right, so you're doing moles of solute per liter of solution. So if they give me grams, I've got to convert those grams to moles before I can find the molarity. And again, you've got to have those two units. You've got to have moles and you've got to have liters to accurately find your molarity. Now, your book gives you lots of examples of questions on how to do that as well, but then they also talk about in section 3.4 how to figure out other solution concentrations. We're not going to spend a whole lot of time on those because, again, 80% of the time in chemistry, molarity is how we're going to express concentration. Now, if you have any questions on anything from this chapter, please reach out and let me know. I am here to help. If there's anything that I can write out for you, or you try a problem, you're not sure if you've got the right answer, just send me a copy of your work. I'll look over it, and then I can send you back a response showing any mistakes that I found. But I hope you enjoy this. I hope you have a calculator handy because you definitely will need it for this chapter. You'll also need a periodic table because you'll have to look up these values, and I'm not expecting you to know these values off the top of your head. But what you'll find in doing your homework is the more you work with certain numbers, the easier they are for you to remember. Have a great rest of your day. Thank you.